Let's look at one last related rates example. Here I have the streetlight problem. This is another classic example that you'll see in every calculus textbook. A streetlight is on the top of a 20-foot pole. So let's just draw that first. Here's my streetlight, and I know that this distance is 20. So how about I call this S for streetlight? So S is 20. A person who is 5 feet tall walks away from the pole. So okay, a person who is 5 feet tall over here. This person, and I'm going to call this height right here, we'll call that P for person, is 5, walks away from the pole, so the person is going in this direction, walks away from the pole at a rate of 5 feet per second. Let's come back to this number here. I want to revisit that later on. At what rate is the person's shadow growing? So, okay, we're talking about the person's shadow. If you think about this street light, it's casting light, it's going to hit this person, and then this distance right here is the shadow. So we have another right triangle. Again, surprise, surprise. Here is, let's see, this distance right here. This represents the person's shadow. So I'm going to call this, I don't want to call it S because I've already used S, so how about I call this X? So it says, at what rate is the person's shadow growing when he is 20 feet from the pole? So this distance right here, he's 20 feet from the pole. I'm going to call this distance Y. So how about I call this Y as 20 feet? So what else do I know here? Let's see, what else do we know? We've used the 20 feet. We used the 5 feet. This rate of 5 feet per second, let's talk about that because that we haven't used. So a person who is 5 feet away, who is 5 feet tall, walks away from the pole at a rate of 5 feet per second. So we said this person is moving in this direction. So this person is moving away from the pole. So that's this distance right here, is moving away from the pole at a rate of 5 feet per second. So that's telling me about the distance between the person and the pole. How is that distance changing over time? So that's telling me about the rate of change of y. So that means that dy dt, this side, right, this person as they walk away, this side right here is getting longer. So that means dy dt should be a positive 5 feet per second. What else do we know or want to know here? It says, at what rate is the person's shadow growing? So we said this represents the person's shadow. We don't know what x is, but again, we could probably figure it out. I'm mostly interested in, though, is the rate at which the person's shadow is growing. So I'm interested in how is this side changing. So what is dx over dt? How is that side changing? So this is what I'm after. What is dx dt? If I can figure that out, I'll figure my problem out. Just to give a few more derivatives, this streetlight right here, we said that was 20 feet tall. That height is not changing, right? The street light isn't getting longer or shorter. So let's say that ds dt is equal to 0, just so that we have that. This person right here is also, well, let's assume that they're not growing or shrinking in any measurable or distinct or significant way. So we'll say for that, we'll say dp dt is equal to 0. So I need some sort of relationship that involves x. Let's see, what else can I use? I can use y, I can use s, I can use p. And some of you might look at this and say, okay, well, I see a right triangle. I'm thinking about Pythagorean Theorem. We could use a squared plus b squared equals c squared. The problem with that is that we don't really know anything about this side here. If I wanted to talk about that, And I could create an equation that relates, A, B, and C, but I don't think it's particularly helpful because we don't know anything about that hypotenuse. We don't know how it's changing because the hypotenuse is also going to change. So that's not really going to help us. This one's kind of tricky, I think, because it's not quite as obvious here. The relationship that we want to use between all these variables is perhaps not quite as obvious as the other examples that we've looked at so far. What I really have right here, this is actually a right triangle. And if I draw this bigger triangle, right, that bigger triangle contains, so to speak, that smaller triangle. What I have here is two similar triangles. I have the yellow triangle, which I've drawn right there, and let me maybe highlight in red. Here's the red triangle. The yellow triangle and the red triangle are similar triangles. And what do I know about similar triangles? Well, I know that similar triangles are proportional. So that means I can set up this ratio of sides here. I can set up this ratio of sides between the big triangle, the red triangle, and the little triangle, the yellow one. So I'm going to do just that. I'm going to set up this relationship between the big triangle red and the small triangle yellow. So let's start with the big triangle red here. And I'm going to start with s equals 20 just because that sticks out at me. I'm going to talk about the vertical side of that red triangle. So s divided by, I want to relate that to the vertical side of the smaller triangle. And that, in this case, that would be p. So s divided by p is equal to, now I'd like to talk about this horizontal side over here. And the tricky part about this is that that horizontal side I don't have one variable to talk about that. I have y and I have x. But I know that if I want to talk about this whole side right here, I should take y and x and add them together. So the horizontal side of the big triangle, of the red triangle, I should have x plus y divided by, well, what's the horizontal side of the smaller triangle? It's just x. So x plus y over x. So what we're doing here is we're talking about, and let me just kind of restate where this equation is coming from. This s is the vertical side of my larger triangle, and I am creating a ratio between the vertical side of the big triangle and the vertical side of the small triangle. P is equal to, okay, now I have another ratio over here. Now I have the horizontal side of the bigger triangle, of that red triangle, divided by the horizontal side of the smaller triangle, of that yellow triangle. So all I did here was set up a proportion. And I could, if I wanted to, I look at s and I look at p, look at those derivatives. ds dt is 0, dp dt is 0. Remember that if those derivatives are 0, we can plug in s and p before we take the derivative. So because those sides are not changing, I can say, well, s, that's really 20, divided by p, that's actually 5. I can't do that for x and y over here. I can't do that for x because then I would be assuming that dx dt is equal to 0, and I don't know that. That's what I'm trying to find out. And I can't do that for y. Oops, I can't do that for y because dy dt is not 0. dy dt is 5. So I can't just plug 20 in for y yet. I need to wait until I take the derivative. So 20 over 5 equals x plus y divided by x. 20 over 5, that's really 4, equals x plus y over x. And I could go ahead and take the denominator or take the derivative right now if I really wanted to, but I'm looking at this side and side looks a little bit ugly. Because if I wanted to take the derivative of that right-hand side, I'd be stuck using the quotient rule. And like I said, hey, if I have a choice between using the quotient rule and not using the quotient rule, well, I'm going to choose to not use the quotient rule if I can get around it somehow, some way. So before I take the derivative, I'm just going to algebraically manipulate this equation, because I can still use algebra. I'm going to multiply both sides by x. On the right-hand side, those will cancel. I'll just be left with x plus y. And on the right-hand side, 4 times x, I'll have 4x. Now this is a whole lot easier for me to take the derivative of. And if I wanted to make it even easier, I can just, well, let's subtract x from both sides. Now I have 3x is equal to y. This is a really nice equation to work with because now I just have two terms. It's a power rule on both of them. There's no other derivative rules that are necessary. So what I'm going to do is I'm going to take the derivative with respect to time, remembering that I need implicit differentiation. I need my chain rule here. So the derivative of 3x of that left-hand side, derivative of 3x would just be 3. But I'm taking the derivative with respect to time, so I need to multiply that by dx over dt is equal to, on the right-hand side, well, the derivative of y is simply just 1. But again, I'm taking the derivative with respect to time. I'm using my implicit differentiation, so I need to multiply by dy over dt. So I have 3 dx dt is equal to dy over dt. So this is a pretty nice simple equation, but let's go back to our problem. Let's go back to our drawing and remember, what are we even looking for here? Remember, we're looking for the thing we want to find. What is dx dt? That's what we want to know. And we know that dy dt is a positive 5. So let's see, if I take positive 5 and plug that in for dy dt, I have 3 dx dt is equal to a positive 5. So that means dx dt is 5 over 3, which would be, what, about 1.6 repeating if you really want a decimal approximation. I also want to give a unit here. So what are our units of x? Remember, x up here measured distance. X was a measure of distance, and we measured distance in feet. So let's see, I have 5/3 feet per, what is my unit of time? What's my unit of time of t? Let's see, feet per second. I see that per second. That is my unit of time. So 5/3 feet per second, or 1.6 repeating feet per second, is the rate of change of that person's shadow. Let's maybe go back then and check, hey, is that right? We ended up with a positive answer, even though it's not written there. It's really a positive 5/3 or a positive 1.6 repeating. Is that reasonable for us? Well, if I go back and look, remember we said the person is walking away from the pole, so this person is walking further away. So if this person is now, let's say, over here, is that person's shadow going to be longer, or is that person's shadow going to be shorter? This might require a little bit of measuring on your part, but this is the person's shadow. That looks a whole lot longer to me than this side x is. So yes, the person's shadow is getting longer. That's actually even just like an experiment that you can perform at home. If you walk away from a light, or if you move an object away from the light, the shadow that object casts is going to get longer. So that means that the rate of change of the person's shadow is 5/3 feet per second, or 1.6 repeating feet per second.